Hi, this is Compiler Design Lecture 1. Before we start, let's understand what is a compiler. But before we understand what is a compiler, let's understand what is an interpreter. Well, consider a machine. I draw this machine with these kind of squiggly lines. What is a machine? Well, a Turing machine, if you know what is a Turing machine, is a machine. A hardware machine like the Intel x86 machine is a machine. A mobile phone that can compute something is a machine. Essentially, any computer is a machine. In fact, even a Java virtual machine is a machine. All right. So, what is a machine? What is a computing machine? On a computing machine, you can run a program which has some instructions, and I'm going to call these instructions the low-level instructions. So, a program with low-level instructions can execute on such a machine. However, there is a problem. This program with low-level instructions is too hard for humans to understand and program because these instructions are low-level. Okay. So typically what could be done, or what was done in the early days of computing, was that people invented high-level instructions. So the machine remains the same, whatever it is. Maybe it's a Java virtual machine, or maybe it's an Intel x86 machine. But then they would invent a new language or a new machine which kind of executes on top of this low-level machine, and the instructions of this high-level machine would be higher level than the low-level machines, and so the program would require high-level instructions. Now, because this high-level instructions do not actually cannot actually execute directly on the low-level machine, because the low-level machine implements low-level instructions, we need something in the middle, and that something in the middle could be the interpreter. The interpreter itself should be able to execute on the low-level machine, right? So the interpreter itself needs to be implemented using the low-level instructions. But the interpreter should be able to interpret these high-level instructions of the high-level program, of the high-level programming language. Okay, so typically how an interpreter works is it fetches the next instruction from the high-level program, interprets it, executes it, and then moves to the next high-level instruction, and so on. Okay. So while an interpreter is executing, it takes kind of two inputs. One is the program with the high-level instructions that we already saw in the picture, but it also needs some input data to basically execute. And then as it executes, it generates some output. Maybe it prints something to the screen, maybe it sends some commands to the printer or whatever. Okay, so we understand the pictorial representation of interpreter, but let's try to, understand what is an interpreter in a functional form. So you can think of interpret, the function of an interpreter, to be a function that takes two arguments, program and data. The program here is the program in high-level instructions, and the data is whatever the data the user gives, and it generates an output. Okay, and recall that an output could be either some print statements on the console, or it could be output to the printer, or whatever else. Okay, so importantly, the interpreter itself needs to be implemented using low-level instructions so it can execute on the machine, whereas the program that executes would be written in the high level using high-level instructions. That's the whole need of the interpreter. Okay, so to basically represent this more precisely, I'm using these annotations in red. LL stands for low level and HL stands for high level. And so the interpreter itself is written in low level instructions, while the program is written using high level instructions. Now, it is possible to write the interpret function here slightly differently. Instead of saying that it takes two arguments, program and data, how about we stage these arguments? We say first it takes program and returns a function that takes data and returns output, right? So this is also called currying the inputs of the function. So instead of taking both arguments at once, we kind of stage this and say, let's take the program first, and what is the interpreter is going to do is it's going to return another function that would be able to take data and generate output. All right. Now it makes sense to curry the arguments of interpret this way because typically the same program is executed on several different types of data or values of data. Okay, So I want to again emphasize that we would like to probably represent our interpret function in this manner, where it first takes program and then returns a function that takes data and returns the output. Right? Okay. Now that we understand this representation of the interpreter function, let's understand what is a compile function, or what is a compiler. Now, many of you must have used a compiler, and typically we understand a compiler as something that takes a high-level program and returns an executable. The executable itself should be able to execute or run on the machine itself. So the executable itself needs to be written, needs to be a program that uses low-level instructions, right? And what is the executable? Well, the executable when run on the machine would take data and return output, just like before. Now notice here that these functions, data to output, are kind of identical in both these functions, right? And so in a way, when we apply the interpreter on the high-level program to get a function that takes data and returns output, we are basically generating an executable, right? So when we apply the interpreter on the program, we generate an executable, sort of, right? At least the functional representation seems to say that. Okay. Yeah. So once again, what is low level and what is high level? The interpret function is low level, must be low level, it should be executable on the machine. But the input program is high level. Similarly, the compile function needs to be low level because it needs to execute on the machine. The executable needs to be low level because it also needs to execute on the machine. All right. And we say that, look, when we apply interpret on the high level program, what we get actually is the executable, because both the return functions in the first case and in the second case are doing the same thing. They take data and return output. Another way to say this is that the executable is a specialization of the interpreter on the program. All right. So what do I mean by specialization? Well, I'm going to define that more formally in the next slide. But basically, think about it that one program is applied partially on one of the inputs, so that you get another program which is a specialized version of that on the first program on a given input. All right. So more precisely, this is also called partial evaluation or specialization. So let's say there is a function prog that takes two inputs. I'm just dividing the two inputs into two parts. One is the static part, I static, and one is the dynamic part, I dynamic, and it returns an output. All right. A partial evaluation, let's say the static part is static across several runs. So what you can do is you can partially evaluate prog on the static part to get a new program, prog star, that just takes I dynamic and not I static, because I static has already been folded into prog star and then returns the output. All right. So we say that prog star is the residual program, and obtained by partially evaluating or specializing prog on I static. Now, what is the advantage of specialization or partial evaluation? Well, this makes sense only if prog star is hopefully faster or in some ways better, maybe shorter than the original program. All right. And if that's true, then this is a good thing to do, because then you can partially evaluate prog star once, and then you can execute prog star on I dynamic 100 different times, and each of the 100 times it's going to be slightly faster than executing the original program on both I static and I dynamic. So here is the crux of the lecture, and this is also called the first Fujamura projection. There are actually 3 Fujamura projections. We are not going to go through the second and third Fujamura projections. They're not relevant to the course. But the first Fujamura projection says specializing an interpreter for a given source code. What is source code? Source code is another name for a high-level program. Yields an executable. And this is exactly what we saw in our previous slide. So think about the interpret function, which takes a program and returns another function that takes data and returns output. And think about a specializer function that takes both interpret and program, and it yields a function which is the executable, which takes data and generates output. Recall that an executable is nothing but a function that takes data and generates output, right? And so interpret can be thought of as a function that takes in a program and generates an executable. And you could specialize this, and so you can specialize the interpreter on a program to generate an executable. All right. So partial evaluation of the interpreter over the high-level program yields the executable. Now, the partial evaluation of the interpreter on the program yields an executable, and once again, this is meaningful only if executing the executable on 100 different input data is faster than executing the original interpreter on both the program and the data. Right? Notice that one trivial way to specialize the interpreter on the high-level program or the source code is to just put the whole entire interpreter code and the high-level program in a single file and call it the executable. All right? And then say that this executable is just going to execute the first part, which is the interpreter, on the second part, which is the high-level program, both of which are part of the executable. But this type of specialization is not any beneficial, although it is still a specialization. We would like to do something better, right? And that's exactly what is compilation. And in many ways, the quality of compilation depends on how much faster is the specialized program, the executable, compared to the original interpreted program, interpreter program that would have interpreted the entire program from scratch, right? Okay, just for completeness, I list the second and third Fujamura projections on the slide. I'm not going to go through these in the lecture, but you are free to look through them if you're interested. All right, so takeaways from the first Fujamura projection. The executable is a partial evaluation of the interpreter on the program source code. A compilation is this process of partial evaluation. And this makes sense only if the executable runs faster than the execution of the original interpreter on the input program.